Hey everybody, it's Mrs. Harbin. Just getting video notes 1.3 done with you. We're going to look at 1, 2, 3, 4, 5 objectives for this, and we're finishing up the unit with nuclear chemistry. Alright, if you want to read it all, chapter 25 gives you so much information about nuclear chem. You will not be disappointed. I think you're going to like it. Alright, so what is an isotope? We already know. And we've been working on these. So this is isotopic notation. This is isotope name. Look, there's 3 isotopes of carbon here. So it's all carbon all day, 6 protons. But what's different about them is that there's different number of neutrons in each of these isotopes. So isotopes are atoms, and isotopes of each other have different number of neutrons than the other isotopes. So this is a carbon 12 isotope, carbon 13, carbon 14. They all have 6 protons or it wouldn't be carbon. But carbon 13 has 7 neutrons, carbon 12 has 6 neutrons, and carbon 14 has 8 neutrons. Okay. Alright, so some isotopes are unstable. What does that mean, unstable? Okay, because the nucleus has protons and neutrons always, you're putting things with positive charge together. Positive things should repel each other, but in a nucleus, those positive things stay together. So, let's see why. The subatomic particles in the nucleus have a force in between them called the strong nuclear force. So there's several fundamental forces in that scientists have explained, like gravity, electrostatic force. Strong nuclear force is one of those main forces that acts in our known universe. So the strong nuclear force holds protons next to protons, neutrons next to neutrons, and neutrons next to protons. So it acts between tiny particles when they're certain distances from each other, and it holds them together. So what does radioactive mean? Well, radioactive means unstable. So let's look at what is stable. Band of stability. This is called the band of stability. This whole thing is a graph of the band of stability, but the actual band are these dots. Each dot is a stable nucleus, or a stable isotope, same thing, which the strong force works well. So each dot, those are not radioactive isotopes. So atomic number 20 with 24 neutrons, this is a stable isotope. It is not radioactive. But what about an isotope that has 20 protons, but only, let's say, 16 neutrons? Well, this is not one of these dots, so this is an unstable nucleus. So an isotope that's not one of these dots, an atom that's not one of those dots, is not stable. So things that aren't stable, nuclei that aren't stable, will decay spontaneously. That's what radioactivity is spontaneous radioactive decay. That's one form of radioactivity. This is the letter, Greek letter A. This is alpha. A is alpha. Alpha decay looks like this. If you're representing it on paper, it has a number 4 up here and a 2 here. So that means it has a mass number 4 and an atomic number of 2. The other thing you might see, and you should write this down, is 42He, because what an alpha particle really is 2 protons and 2 neutrons. Okay? What has 2 protons and 2 neutrons almost all the time? A helium nucleus. Okay. Alpha particles are pretty heavy as terms of radioactivity. Alpha particles have positive charge. It doesn't have much penetrating power, which means your skin can block it from entering your body. It does cause damage on a small level, though, because it's heavy. If it hit a cell, it would cause damage. If it just hits your skin, it's blocked. All right. So this is a nuclear equation, and a nuclear equation is a way of representing what happens during a nuclear reaction. So this is lawrencium-256. It is radioactive. So it gives off an alpha particle. There's your alpha particle. And your alpha particle also, when lawrencium decays, it makes a new particle. So we need to find out what that new particle is. So we need the atomic number. I'm sorry, the atomic number is Z. So if there's 103 on the left side of this arrow, there needs to be a total of 103 on the right side. So we already have 2, so that Z is going to be 101. So I'll write it over here. top number. That's 256 on the left side of the arrow. So this total top needs to be 256. So let's make it 252. So when you add it to 4, it's 256. Now, how do I know what symbol is there? You won't find X on the periodic table, but if you look up 101, you'll find MD. So this is what goes there. This is called a spontaneous nuclear decay reaction. It's also called alpha production or alpha decay. Oh, look, it's polonium-151. It goes through alpha decay, so you can write a 4,2-HE right away because I tell you it goes through alpha decay. Then how do I know what the rest of it is? Well, if this is 67, this has to be 65. 151, this needs to be a 147. If I add those up, I get 151. Then how do I know what symbol to put? Well, I look up on the periodic table, and I find out that atomic number 65 is TB. So this is another alpha decay. All right. Hey, what about if it doesn't give off alpha radiation? Well, there's also called beta decay. Beta. Beta. It looks like a 0 and a -1e, or 0, -1 beta, right? Because it's really equivalent to an electron. Okay, so E for electron, -1 for charge, 0 for mass. So basically, a beta decay is when a nucleus is unstable, so some changes happen, and out of that nucleus shoots a beta particle. It's very light, almost massless compared to other things because it's an electron, and electrons have small mass. Okay, it's negatively charged, and because it has a little more energy than an alpha particle, you need metal and other things to block it. Okay. So, oh look, it's a nuclear equation. AM247. Should we have a Z there? No, Mrs. Harbin. We should have a 95. How do I know periodic table atomic number for AM? Here's the beta particle. Right? It's after the arrow because it comes shooting out of this nucleus. And so then we could fill in what element goes here. So this is 95, this is -1. That Z has to be a 96, and that top number needs to be a 247. And so you get CM as the particle that goes there. All right. What about this one? It's gold 211. Gold 211 goes through beta decay. So then this is going to turn into an 80, and this is going to be a 211. How do I know what element to put? I use a periodic table. I find out 80 is mercury. And then you also have to include your beta particle. So 80 plus -1 gives us 79. So the bottom total and the top total equal the bottom total and the top total. Beta decay. Hey, Homer. All right, gamma radiation. This is one you might have heard of, but it looks like that. It's like a little check mark or dive bombing fish, or you know, it looks like that. And you put a 00 there because it's massless, and so it has no mass, so you put a 00. It's just high-speed energy. It has no charge, but because it's high-speed energy, it gets through a lot of things, and it turns people into the Hulk. Okay, so that's just, you know, a cartoon, but that's what they say gamma radiation did. Okay, this is radon 230. It undergoes beta and gamma decay. So you can start with Rn 230, and then what you would look for is the bottom number, so you need a periodic table. And then after you have a periodic table, you would put a 0 and a -1e for your beta, and you'd put your gamma radiation, which isn't going to change the numbers, and then you're going to have a top number. That top number is going to be 230 because on the left and the right it has to equal 230. This bottom number, if I could find a periodic table, the bottom number would represent the atomic number of radon, which happens to be 86. So then the bottom number over here would have to be 87 because it has to equal 86. And then you look up element 87 and you find out that that is francium, Fr. All right. So how do I know this is beta and gamma? Well, there's your beta and there's your gamma. Okay. We'll save this one for class, erbium. All right. All right. So we've done the 3 types of spontaneous nuclear decay. So what happens? Why do things do that? Well, sometimes a nucleus could have too many things in it. Too many protons, too many neutrons, too many of both. Okay, so if something has 10 protons and 15 neutrons, we're at 10 and 15, we're right about there. Oh, that looks pretty stable, so it's not going to decay. Stable. All right. What if it has 40 protons and 20 neutrons? It's over here. So if that happens, I like, uh-oh, it's not a dot in the band, so radioactive. Radioactive. All right. 70 protons and 130 neutrons. We're way up here. Uh-oh, radioactive. All right. What if it has bigger than 83 protons? So right here, guess what? No stable isotopes. Those are all going to be radioactive. So what makes things radioactive? Too many protons, too many neutrons, too many protons and neutrons, so that strong force can't work. All right, so when we talked about gamma radiation, we were looking at this end of the electromagnetic spectrum. So here's visible light, here's microwaves, here's X-rays. If you notice, gamma rays are at the really high energy side of the electromagnetic spectrum. Okay, that's why they can penetrate through many things, and they can cause damage to cells and other things. Okay, radioactive decay. You can't speed it up, you can't slow it down, you can't control it, so you study it. We study it to help explain it. So half-life is one thing that relates to radioactive decay. Half-life is a time. Did I say half-life is a time? Because it is. Half-life is the time it takes for a radioactive sample to decay to half its original, to half its original amount. What does that mean? That means if I had 100 radioactive isotopes, look, 100 of them. When I counted how many I had that were not radioactive anymore, and it was half left, this time would be the half-life. Okay? So, here are the half-lives of some radioactive isotopes. It's pretty interesting to note that tritium is an isotope of hydrogen that's radioactive. It gives off beta radiation, and if I had 1 gram of it today, in 12.33 years, I would have half a gram of that left. The rest of those isotopes will have turned into a different nucleus. All right. Look at carbon-14, has a half-life of 5,730 years, which helps us date stuff that was once living. Okay. So all of these are radioactive. Here are the isotope names and symbols, and then here's the kind of radiation they give off: beta, gamma, alpha. And here's their half-lives. Okay. So organic things that are made from carbon decay by half-life. So if you take a deep breath in and then exhale, you are maintaining, anytime you're still living, you're maintaining a ratio of carbon-14 to carbon-12 that continuously replenishes, and that's constant in your body when you're living. Same with trees, same with plants, same with animals. The ratio of carbon-12 to carbon-14 is constant. But carbon-14 is radioactive. So when something ceases to be living and growing, or ceases to be living like a plant or an animal, then the carbon-14 starts to radioactively decay and is not replenishing anymore. So you can figure out how old a body is if it's pretty old. Maybe decide how old clothing is from a long time ago because it was made from plants. How old parts of houses were that were made from plants if they're pretty old, because you can compare the ratio of carbon-14 to carbon-12 in the old thing to the ratio of when things are living. Okay, so half-life, we can apply some calculations. So here's zirconium-84. It's 26 minutes. So I say T1/2 for half-life. If you start with 175 grams, how much is going to be left after 104 minutes? Alright, so every 26 minutes, zirconium-84 reduces to half its original amount. Half of the atoms radioactively decay. So in 104 minutes, if I take every 26 minutes for it to radioactively decay, then that means 4 half-lives go by in 104 minutes. Well, 4 half-lives go by, my 175 grams is going to cut in half after the first 26 minutes, and then half of it's going to decay after the next 26 minutes, and then the next 26 minutes, and then the fourth set of 26 minutes. So I'm going to end up with 10.94 grams of zirconium-84. Alright, let's look at this one. Barium's half-life is 12 days. So every 12 days, barium-131 radioactively decays to half its original amount. How many grams left after 72 days if 20 grams is what you're starting with? So 20 grams is our start. After 72 days, every 12 days, a half-life happens. So after 72, there's going to be, 6. who can divide here, Mrs. Harbin? So 6 half-lives are going to go by. 6 half-lives. So if 20 grams goes through 6 half-lives, it's going to cut in half. How many times? 6 times. You got it. Oops, divided by 2. 1, 2, 3, 4, 5, 6. Which means after 72 days, there's going to be 0.313 grams left of that barium-131. Okay, moving on to more ways to calculate using half-life. So we have 100 grams of carbon-14 and one day, and then some other day we only have 25 grams left. All right, how long after that? 11,460 years. Wow, that's a long time. So we want to know what the half-life is. Okay, here's total time. Total time. All right. So we want to know how long each half-life is. Well, we have to know how much is decayed. So we start with our grams and we cut it in half. That gives us to 50 grams. But our sample says we have 25 grams left. So I take my mass and I cut it in half until I have the final mass. That's 25 grams. So what does that mean? That means that the 100 grams goes through 2 half-lives to get to 25 grams. So 2 half-lives have passed. 2 half-lives. All right. So then in my 11,460 years, my carbon has decayed twice. It's gone through 2 half-lives. And so that means that each half-life must have been 5,730 years. Okay. I'm going to save this one for class to practice. Okay. Fission and fusion, the last topic we're going to do today. Fusion. All right, fusion, nuclear fusion, it was 2 small particles collide and they make a larger particle, some neutrons and some energy. So you start with 2 small nuclei, you speed them up really fast, you mush them together and they stay together. That's called fusion. Okay. Fission is when you start with a big nucleus and you shoot it with a neutron. And that nucleus makes smaller particles. That means it splits, okay? And it splits and gives off a lot of energy and some neutrons. So this is uranium-235. 235, 92. So it's got a big nucleus, 235 total things in that nucleus. You hit it with a neutron. Uh-oh, which one of these says hit with a neutron? Fission. This must be fission. What it does is it breaks up into strontium-90 and 2 more neutrons. But this isn't balanced yet. There's a missing piece. So we could figure it out. Our top number is 235 plus 1 is 236. So our top number over here needs to be 236. Now there's 2 neutrons. So there's 2 of these and a mass of 1 each. So there's 2. So 90 plus 2 is 92. So whatever's missing has to be the difference between 92 and 236. So I do 236 minus 92. And I get 4, 13 minus 4, 1. So I know that this top number has to be 144, because when I have 144 plus 90 plus 2, I get 236. Right? Then on the bottom, it's 92 over here and 38 here. So I need this bottom number to equal 92. And I already have 38, so I'm going to have to make it be 54. Okay, so 80, 92. All right, so then what do I put in for the symbol? Well, I look up on the periodic table, I find out that's xenon. Okay, so the missing piece is xenon in this fission reaction. How do I know it's fission? I use a neutron to make a big thing split apart. So here's 2 pictures. Which one's fusion? Well, 2 small things make a bigger one. So this is fused together. All right. This is one big thing makes smaller ones, so this is fission, fish apart. Fission splits. All right, so what is fission? It's when a nucleus hits a big nucleus, a neutron hits a big nucleus, splits into smaller ones, and some neutrons. It can cause a chain reaction because more neutrons come off, and those are the bullets that cause the split. So if you look at this next slide, you hit one nucleus and you make a split, and then 2 more neutrons are formed, and so those can hit another nucleus and that can split. You get more neutrons and split, 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 and you get this chain reaction. It's uncontrollable, lots of energy given off, and yes, you can get an explosion. Okay, because of the energy given off, it would cause an explosion. So this is called a chain reaction. All right, so fission and fusion facts. That's very alliterative. Fusion is hard to start. You're trying to get these 2 positive tiny things to mush together and make something big. But nuclei are positive, they're going to repel each other. So it's really hard to start fusion. You need things like the sun to do it. Okay. Fission is easier to start since a neutron's neutral, and so you can shoot it at a nucleus and it's not going to repel. So fission is a little easier to start. They've used fission for nuclear power and for bombs. Fusion is happening in the sun right now. Thank you, fusion. And so you can do a fission reaction to start a fusion reaction, and that's one kind of application. Not the best application because it's a bomb, but anyway. Okay, so just to review. Alpha particles are big, heavy, and positive. Okay. Beta particles are lighter, kind of like electrons. Oops, you don't need to know this one. Alright, so you're not, it's true, but you don't need to know it. Gamma is massless, but it can get through stuff. If it's on the band of stability, it's stable. If it's off, it's not. Half-life, you keep cutting your mass in half. Fission splits, fusion sticks. Alright, read chapter 25, Welcome to the New Age. Learn a lot of chem. 5 objectives. I know this is long, but it's radioactive, peeps. Peace out.